Hello everyone, here is ESTR 1004 project. We are Charmanders. My name is Yuleten and our project name is Planimeter. Planimeter is a drafting instrument to measure the area by tracing the boundary. And we look at this planimeter as a polar planimeter. And this is the pole, which is the fixed point, and this is the pole arm, this is the tracer arm, and this is a pointer. A knot is connecting the two arms, thus making it movable, and it can be any angles between the two arms. The pointer will move around the curve, and at the end, the carriage will show the area of this region. The wheel will mark the length of the curve, which is perpendicular to the tracer arm. When explaining its mechanism, we can use the Green theorem. We have learned the Green theorem in the keep video, and here we will have a review. We assume that R is any closed bounded region in the xy plane whose boundary C consists of finitely many smooth curves. F1 and F2 are any continuous functions with continuous partial f, partial f1 over partial y, and partial f2 over partial x everywhere in some domain containing the region R. Then here is the Green theorem. Its formula is the below one. The Green theorem relates the double integral to the line integral, which is very useful. And then we will move to the mechanism of planimeter. And this picture is the planimeter in the xy plane. The polar planimeter has the shape of a ruler with two legs. One leg of length R connects the orange 0, to AB. The other leg of length R connects AB with XY, which is OE and EM respectively. During the measurement process, the planimeter is fixed at 0, and the point xy is located at the boundary of the region. If xy is given, then AB is determined as an intersection point of two circles of radius r, 0, and xy. If we require that the angle between the two legs of the planimeter is smaller than pi, then the intersection point is uniquely determined. Namely, AB are functions of x and y. The measurement consists of dragging the endpoint xy along the boundary of the region R. A wheel attached to the second arm measure is the motion of xy in the direction orthogonal to the leg. After completing the path along the boundary, the total wheel rotation indicates the area of the region. Then we will introduce the derivation of planimeter. Let's first introduce its general condition. Considering the vector field fxy, which is b minus y over r and x minus a over r, when we assume r is equal to 1, which is achievable when building a planimeter, the vector field f becomes b minus y x minus a. and the vector field is perpendicular to the arm EM, because EM and F's dot product is 0. As EM is equal to OE and they are both equal to R, we have the below formulas. Then we substitute this into the Green theorem formula, and we will get the left side is equal to the double integral of 2 plus the curl of m dx dy for region R. Here the curl m is equal to -1 because m is equal to the vector minus b and a. As a result, the left side is equal to dx dy over region R. Oh, sorry, here is a mistake. It should be the double integral. And so the left side is equal to the area A. We can use this principle to measure the area when using a real planimeter. Then we will introduce the principle of our program. It is a little bit different from the real planimeter, but still we can use the Green's theorem. Here we choose f1 as -y and f2 as x. So because both f1 and f2 can be randomly selected, so we can derive that the line integral is equal to the left side, which is 2dA. So in the program, the area A is equal to half of the line integral. If we give the function of x and y with respect to t, the program can compute the area of the curve. To achieve this, we introduce an expression tree. After using it, we can easily type any functions such as sine, cosine, and so on. And here is the main code, which is the integral part. Here we choose d as 0.000001, and we approximate dx and dy to be the d. Then we just compute y dx, x dy, and when finishing it, we can get the area. And then here is the running result of our program. We just choose some easy functions such as the curve of a circle and the curve of a square. But if you want to compute the area of other curves, it is also achievable because our program can support a various kind of expressions and functions. Actually, our project have done more than this. We've just introduced a program to compute the area given the parametric functions of the curve, It can be any function, for example, sine, cosine, line, and polynomial functions. And here is a program. You can have a look. We will skip the running part because of the time limit. Besides this, we've also built a SolidWorks model of Planimeter. If correctly built, the model can be a real one after 3D printing. Also, we've using Python codes which can transfer a picture of curve into a matrix. It can be used to estimate the area by counting the quantities of zero inside the curve. In the matrix, the position where the curve exists is marked as a number bigger than zero, which indicates its color. The blank area is marked as zero. We can also directly integrate the curve considering each element as a unit whose length is 1. Under the circumstances, both dx and dy in the program should be 1. So actually the method cannot compute the exact area of a curve in the picture because we don't know its size. But if given the actual size, the program is still achievable. But we don't focus on this one. Besides, to make our program more user-friendly, we use an open source software which can transfer a function of the curve into a picture. For example, if we type the function of a circle, we are able to show a picture of the circle on the screen. The result can be shown during the presentation. Okay, that's all. Thanks for listening. Hopefully you will enjoy our project Planimeter. Goodbye.